When I was a kid, I always loved playing with Legos. I had a bunch of sets of Legos, and they would always come with pieces, and they would come with an instruction booklet. And from that, you knew that in this case, what you were going to get was the 2002 Ultimate Collector's Edition Lego Yoda. That's right. Now, this is actually an apt analogy for some of the mathematics that I enjoy thinking about. I want to explain that to you, so consider this, a wiggled circle, by which I mean just the black outline, not the interior of it. If you want to think about it as being built out of Legos, being built out of pieces, what you can do is you can cut it along, in this case, 3 horizontal lines. When you cut it up to sort of wiggling in the horizontal direction, you see that you get this representation of it in pieces, where you just glue them in the natural way, and that will give you back the original shape. Now, if I gave this to you as a Lego set, what you would see is something more like this. And I would have to give you the instruction booklet from which you could recreate the original wiggled circle. So for wiggled circles, it turns out if you chop them up with enough horizontal lines, there's only 3 types of pieces that you need: a frown, a vertical line, and a smiley face. But as mathematicians, we like doing things a little bit more complicated, so we move on to the case of surfaces floating around in 3 dimensions. Now you can try to play the same game and think about these as built out of pieces. So we cut along horizontal planes now instead of horizontal lines, and when we do that, we get a decomposition of that surface into pieces like this. For any surface that's floating around in 3 dimensions, if you chop it with enough horizontal planes, then you can always show that you'll get these 5 types of pieces: the green cap, the brown bowl, the purple, we call this technical term, pair of pants, because you can imagine getting into it. The orange upside down version, and I didn't have this in my example, but you can also get cylinders. So what, you might ask? Well, it turns out that these pieces have a lot of information. So you might notice that the surface that I drew before had 1 hole going through it. And you can ask, well, I have the pieces and how they glue together. Is there a way that I could have known that there was going to be 1 hole? It turns out that there's actually a formula for the number of holes. If I take 1 plus a half times the quantity, I count the number of orange pieces I have, I add that to the number of purple pieces I have, I subtract the number of green pieces I have, and I subtract the number of brown pieces I have, then I get the number of holes. So in our example, we see that there's 1 orange piece plus 2 purple pieces minus 1 green piece minus 2 brown pieces. So the thing in parentheses, 1 plus 2 minus 1 minus 2, that's 0. And I see that extra 1 tells me that I have 1 hole. Okay, now I really do think about these things. This is a picture that I took of my blackboard a few weeks ago, and you can see right at the top there is something that kind of looks like these decompositions. But it would be a lie if I stopped there. It turns out that these pieces that I think about have some extra structure, which is called contact geometry. Now, to describe contact geometry would take another 5-minute talk, but I'll give you a basic idea. So if you're driving a car along, so here we see a car parallel parking, it's constrained to move in the direction that the wheels are facing. So if you're driving along, you can't suddenly slide to the left or slide to the right. That kind of constrained geometry is what we call contact geometry. So if the pieces I described before were Legos, you might then wonder, if I want to study this contact geometry and build it out of pieces, what do those pieces look like? Well, this is what I studied in my thesis. And it turns out that you can actually understand exactly what those pieces look like. And I've drawn them here as connects, another building block which you might be familiar with, something that I also loved playing with. Not only do I understand what the pieces look like, but I also understand what the possible instruction books can look like. So I understand how those pieces can possibly glue together. Okay, so what? Well, as a contact geometer, I'm interested in very subtle invariance of these contact spaces. So before we could see the number of holes from the number of pieces, I'm interested in getting numbers, much more subtle than that, out of understanding how these pieces glue together. And that's what my research, a lot of my research, is currently about. So I leave you with this, a picture of me as a preteen studying one of my first contact manifolds. Thank you very much.